So I made this for another part. You have already seen me in the last session how I have generated a sawtooth waveform. I've used sine in a sine function of sine of 2 pi f into t, where t is the clock there. So this is how I have used there. So a sine will give repeating sequence. Not only that, even a reminder function will give the same thing, or a m. I've just added this 1 by fs to by 1 by fs. I've just made this because I want to do manipulation to this one. Even for sawtooth, I just want to do that. That's why I just gave. Ignore that. You can. This itself is sufficient for you for a ramp function. So out of your switching frequency, every time it has to reset the thing. It has to go for that. So your sawtooth will have your fundamental component. It is like 0 to, not fundamental component. It is 0 to 10 kilohertz. That means 1 by 10k. So it's going to have a frequency like this. Later on, again, it is going to repeat the same thing. It is going to repeat the same thing. So with this sawtooth, we are going to compare T1, T2, I mean TA, TB, TC and all. These are the things we are going to compare. So this is what I said. Here itself I told you. So you have TA, TB, TC and so on, TD. So for initially TA it has to be T0 by 4, which you have obtained there itself. Which you have obtained here itself. T0, T1, T2 we have obtained here. Now T0 by 4 initially I have given. That means at this time. Now what A, B, C has to be? It has to return 0, 0, 0. See, so at this time, if it is TA, that means TA will be again some value. It is going to return that. So at this time, TA, this leg and sector will be selected. Again, first assume that I have chosen my sector, which is sector 1. It's actually not selecting. Okay. So which is, assume that it is a sector 1. My sector is identified. Then from this, my time will be identified. You know how long will it be there? Till it compared with the repeating sequence, this time will be there. This time will be there. T0 by 4. And your leg A, B, C will return whatever the values. If I give 0, 0, 0, it is going to return that. But how I'm going to write the matrix, I can show it to you here. First, you have to compare your time, which is time t. See, this is your time instant, time t. Let us add 1 because by default I need a initial reference as 1. So if my reference is greater than int 1, it again adds an extra value to this. So 1 plus 1. That means out of this 7, initially it is 1. So this sector, it will be 1. So if it is crossed, that means this int 4. If it is crossed T0 by 4, then it has to go to 1 plus 1. That means the switching sequence have to change. It has to go to sector 2. Not sector 2, sorry. Second instant. This one. How I wrote this one means I have arm A, arm B, arm C. If you see for sector 1 in arm A, okay, let us see. In arm A, what are the values you have? 0, 1, 2, 3, 4, 5. 5 ones and 1 0. So that is what I mentioned. 0, 1, 2, 3, 4, 5 ones and 0. This is for A matrix. I mean leg A. What about B? 0, 0, 3 ones and 0, 0. 0, 0, 3 ones and 0, 0. What about sector A, leg C? We have 3 zeros, 1 and 3 zeros. 3 zeros, 1 and 3 zeros. Similarly for sector 2, these are the values. I mean you have only 3. Then in matrix B you will have 5. In again C you will have 1. This is how you have to write. See, the last one represents the sectors, whether it is sector 1, sector 2, sector 3 and all. Whether it is this one, sector 1, 2, 3 and so on. The second one represents the time instant. If initially it is 1, that means by default it will be in sector 1. I think you know this sequence will go. So my sector is 1 initially, then my time instant is 1. So what it is going to give, here I have given a semicolon. Here I have given a full colon. That means the entire first row will go. Let us see that. Suppose let us see a matrix A equal to rand of 5, 4, 3. Let us assume that I have entered a matrix like this. Or for your time instant, I'll go for 3 leg 6, 1, 2, 3, 4, 5, 6, 7. Yeah, 7 moments, 7 times, and 6 sectors. And suppose this is a matrix. If I give A colon, comma, 1, comma, 1. If I give this means whatever the first row that you have, whatever the first column that you have, that's going to come. Press enter. The first column is going to come. Again, it generated random again. Sorry, I have entered 6 here. That means the last column is going to enter 5949 5472. So it is something, the entire column 1, 1. Okay, let us see here itself. I can explain. My sector 1 is identified. So I have given the time instant as 1. Let us assume initially the time instant 1. That means T0 by 4 is selected. Then it will display A as 0, B as 0 and C as 0. That means all the switches will be in 0 position. Okay. Similarly, if your moment is 2, that means if it is greater than int 1, that means now it has entered into T1 by 2 time. I mean, it has crossed the T0 by 4. It has crossed the T0 by 4. Now T1 has to execute. So during this time, it has to give A1 should be 1, B should be 0, C should be 0. A should be 1, B should be 0, B should be 0, C should be 0. You got it? So you can execute this. So in the initial stages for T less than this one, I'm choosing my sector as 1 because if I don't use that command, I'm not getting that. So I just use this command. And you know, my switch is simply SW array, which is my switching array function here. For this one, 1, time T, sector. So the sector number I know, I have actually defined different sectors here. So here is my sector number, here is my time T. Time T will be updated based on my int functions. So initially all these are greater. So when my repeating sequence, which is my sawtooth waveform, if my sawtooth waveform is generally greater than that, that means only 1 will be there. They're all not executed. So my time T will be 1. Time T1 means this one. Initially my sector will be 1. So it is this one. So what it is going to do, all the column matrix 0, 0 and 0. It is going to give that. And for the same sector, my sector is not going to change. Now my time T will be upgraded because I'm going to move from T0 by 4 to T0 by 2, T1 by 2. Into 2 will be compared. As my time is increasing, reference will be, this is going to be compared. That means this condition will be crossed and it is going to move to this compared. Now my time will become 2. Sorry, my time instant will become 2. So if it is 2, that means it is going to be 1, 0 and 0. So in each sector, it is going to move towards this. A sequence will go like this, B sequence will go like this, C sequence will go like this. for sector 1. Okay. Let's go to the simulation. So this is my pulses. So it is called demux. You can use demux here. So from this, I'll get 6 possibilities. S1, S2, S3, S4, S5, S6. Remember how you have to give is, you might have remembered the sequence may be different, like S1, S2, S2 will be like this. But here, S1, S2 should be in the same leg. S3, S4 should be in the same leg. S5, S6 should be in the same leg. You have to use in this sequence. So if you build this, then you can do the simulation. So let me take a 10-minute time so you can try to do the simulation. If you get some queries, you can ask here. Even I used to prefer that a lot, which is, so the space vector, I'm going to wind it here. I gave you the required things. I told you how to take the screenshot. I told you to take screenshots, save them properly in a Word in a sequence format. So if you have every screenshot, then you can do the things. So the next interesting topic is hysteresis current controller. What is this hysteresis current controller? So I have a reference and I have an actual signal. If I'm going to compare, I have an actual signal. Sorry, I have a reference signal. This is my reference signal. And this is my actual signal. Maybe something. So this actual signal, what I do is I'll compare with this. But how do I compare? Whatever the reference signal that I have, I'm going to add some offset to this. Like I will add some plus DC offset and minus DC offset. So it is going to give positive and negative. So these are the two references. If you can see, the blue line is your upper band and this red line is your lower band. And this brown color line is your actual reference. So for this one, I'm going to give a band for this. That means I will add some DC value to this and some DC value to this. Or I will add some DC value and the same amount of DC value I will subtract from the same reference. And interestingly, I have to make sure that my current is going to oscillate between these two ranges only. It is not going to vary much. So how we can do this? So take that reference signal, subtract the actual current from the reference signal, that is your error signal. So assume that this is my, brown color line is my actual signal. Sorry, reference signal. Brown color line is my reference signal. And whatever the actual current that I have, this black color one, assume that it may be some sinusoidal at one instant. This I'm going to subtract from that. So the reference is being subtracted from the actual. From this, assume that if this error crosses positive limit, assume that if this error, whatever the difference is there, from this to this error, whenever it crosses that positive band, plus, let's assume plus h or plus h by 2. Whenever the error is greater than plus h by 2, make your switch 1. If the error signal is greater than h by 2, make your signal 1. At the same time, if the error is less than minus h by 2, make your signal 1. So whenever it crosses this blue color line or it crosses this brown color line, it has to give 1. That means the switch has to go. If you give that, that means at this instance, it's going to toggle like this. We'll see that a proper detail. Actually, if I have this stylus, then I can do the things properly. God. Yeah, for this one. Now let us do this simulation and we'll understand. Assume that the reference signal is again a sinusoidal now. I'll open that. And one more thing here, I have done that small comparison. I don't need property inspector now. See, this is SVPWM, space vector pulse width modulation. The same thing, let me uncomment this, right click, uncomment. We can comment out. See, using space vector modulation, I have given you the signals, right? In sinusoidal pulse width modulation, what is the difference means? With the repeating sequence, you're just going to compare with sinusoidal signal. If it is less than that, it's going to toggle that switch. If it is greater than that, it is going to toggle the below switch. This is SPWM in case of three phase. So you have to give three sinusoidal signals. So if we take this as modulation 1, it has to be initially 0 for the A phase. Obviously, for B phase, it has to be minus 2 pi by 3. So for C phase, it can be, sorry, yeah, it can be plus 2 pi by 3 or minus 4 pi by 3. It is up to you. So by comparing this with the sinusoidal signal, you can generate S1, S2 and all. A lot of people may have confusion between these two. SPWM means you're just going to compare the sinusoidal signal with the repeating sequence. Whereas the space vector modulation, there is a specific format, like you're going to have space vectors, where in that, based on the choosing sector, you're going to initiate your triggering pulses. So it is different, right? But again, I'm using the same, like instead of this function, you can use three sinusoidal signals also. Both are fine. So you can do this simulation. And if you run that, again, it is going to give the similar output. I have this blocking. Okay. So to modulation next, what is connected via switch? Sir, show the simulation results of SCPWM. Okay. I think I showed it, right? This is the simulation results. Line voltage, line phase voltages. You can see the individual phases, even line voltages, and you can apply harmonic spectrum by going here. Tools, if you go to FFT analysis, I think I have added. Make sure that you save that in logging. You have to save it in workspace and you have to click OK. So whatever the things that you have, whether input 1, input 2, input 3, you have to give your switching frequency and you can do the testing so that you can try it on your own. I think the harmonic spectrum, everyone know that. So it is the only difference is whether you are using SPWM or SCPWM, both are fine. You can use any of that. To modulation next, what is connected via switch? Oh, here. Actually, I have used this switch to show you that vector representation. Wait, I'll show you. Uncomment. Callbacks. Stop load function. So applied. Okay. I'll make it as uncomment. I'll comment this. So you can actually see that vector that I have identified. So in that vector, it is going to move. As here in the modulation index, I'm varying from 0 to 5, some randomly. So what does it go? It actually moves. That means I'm slowly increasing the modulation index. That means I'm increasing the sinusoidal reference. You can actually see that it is going to move higher value to higher value like this. You can see the sinusoidal, it is actually 0 to 360. It is a circle. If you place the sinusoidal signal irrespective of time over 360, it is just a circle. So as I'm varying, what I'm doing here, I'm going to vary the modulation index. So obviously it is going to move its sinusoidal magnitude to higher value or lower value. Why I need a variable modulation index means at the time of closed loop, the variable that you have in your hand is your modulation index and time. So this you can see that this is how it is going to rotate and it is going to give that vector. If I just give only one vector, let us give 0.8 itself, and let us try to go for 5. Let's go for 3 itself. Let us run this. So it will execute faster. But actually my laptop is struggling now. I know, I think you know that MATLAB will take so much space as it is an interpreter. See now, for a fixed modulation index, it is going to operate. But you can see that small jerk because it is an average value, right? So in this space vectors, it is going to operate. That means you are going to get a sinusoidal signal in this form. Just for that I made that. Okay, this is your space vector part modulation. So you can see the difference. What is this sinusoidal pulse width modulation to space vector pulse width modulation? You can see the harmonic spectrum and you can analyze that. If you get higher fundamental in sinusoidal pulse width modulation, then you have to properly check the repeating sequence. You have to adjust the repeating sequence. Then you will get actually for a given switching frequency, for a given sinusoidal reference, space vector pulse width modulation will give more fundamental component than sinusoidal pulse width modulation. Okay, that we'll see later. Now it is hysteresis current controller. I think I have it somewhere here. So I've just used only a single leg. Or if you want 3-phase also I have done. Yeah, 3-phase hysteresis current controller. Let me do this because we are just discussing about 3-phase, right? So in a 3-phase, see what I do, this is my current reference. You can say that this is my current reference. And after these 3, I have used some high inductance value because you are giving a current reference. Most of the things, they do compare the current reference only. With respect to current reference and your actual current, they are going to compare that. I have given a very high inductance, which is 50 millihenry. That's literally high. And you can give any resistance of your choice. I just gave one. And from here, I have taken what do you call? If you see the measurements, I have taken this ABC current references. These current references, I gave it here. This is called relay. If you see relay, you can take a screenshot. So I have given a 0.1 band, like as I told you in this one, you have to give some band limit H. So I have given that band limit as 0.1. So if it crosses some value, it has to. So when it has to trigger, whenever it crosses 0.1, it has to give 1, or whenever it is less than minus 0.1, it has to give 0. That we'll see individually why I have given like that. Because of this not function, I just gave it. If you see here, then you can identify this. You have 3 sinusoidal signals and I have 3 sinusoidal currents. Assume that these 3 are displaced with each other by 120 degrees, like 2 into pi by 3. What about this? It will have minus 4 pi by 3 or 2 pi by 3. So these 3 you have to compare with your actual currents. So whenever it passes that band, it has to go, it has to switch that, it has to turn it on. And the same thing, if I start running the simulation, I just want to know how the current waveform is like. You can see that the current waveform is actually being oscillating between some values. Let us zoom this. So this is what I have mentioned there. So whatever I have mentioned here, no, this is what I have generated. So see, this is my actual reference. And here is my plus band value. Here is my minus band value. I have added plus DC to minus DC. Whereas this black color one is your actual current. See, this black, what is your actual current that I have given it here directly to this one. So this is your hysteresis current controller. The controller seems very simple and it is effective also, but a small disadvantage based on this ripple content. If you want to reduce the ripple, you have to use less band here. So let us take 0.01. Apply. You have to use less band here. If you observe that, though I have used less band, you can observe that it is going to it is oscillating beyond the limits. It is not properly working. Do you observe that? So there has to be a compromise between this band and your inductor current. You can say that in whatever the ripple, you have to compromise between the ripple and your this limit value, this band value. If I give maybe 0.05, I think it's still going to cross that. It is still crossing. You can see it's utterly crossing too much. Yeah, it is still crossing. So there has to be a compromise between your ripple in the current and between. So based on adjusting this band limit, you can have that limit. Suppose if I'm going to reduce it even further, then your ripple may not be controlled properly. It is going to be abrupt. So a proper compromise has to be there. You have to adjust that beyond this limit. Maybe beyond this limit. Suppose 0.1 for me, exactly I got this. But if you want go for 0.2, 0.2, I think everywhere it has to be 0.2 now. 0.2 minus 0.2. I should use a variable instead. 0.2 minus 0.2. Actually, it is going to abrupt. I mean, it's going to violate the thing. Every time it is not going to work fine. Here, actually, I made this small thing, like I just only varied this. But what happens is there has to be compromise between your ripple current, whatever this peak to peak that you have, between that and this limit. You cannot go even, you can go for 0 also, right? But for 0, it is not going to work. So there has to be a compromise between that and your switching frequency. This is called switching frequency, you can say. And you can try the same for a half leg. no need to go for this much. Between these two voltage sources, connect a small resistance. Take that, use high inductance value. In series with, I think I have that simulation. This is current controller half leg. Yeah. So this is simple half leg. You have two switches, inductor. I'm taking the inductor current. So whatever the inductor current, I'm subtracting with the reference. Here I'm having some band like 0.1 to minus 0.1. And you can get this results here. You want to see that pulses also. Let us see that pulses, how it is going to trigger. Let us simulate that. Okay. You can see that whenever this is going to cross that, my output is low, or whenever it is going to cross this, output is high. I think I have written wrongly here, but this is the correct format. Even it is not specific, you can go for your own logic also. The current controller is not just this one. Even the space vector modulation, whatever the method that I told you, it is not the only one. There are so many methods in terms of reference generation, in terms of time predictions. There are so many methods for that. But for the same space vector modulation. Similarly, it is not mandatory that you have to choose a specific limit. You can have your own upper and lower limits also. That is up to you. You can go, even you can do the same logic, or you can violate this logic also. So if you do that, you're going to get your proper output. You can see that my current is going to oscillate between the specific values like this. And if you want to see the harmonic content, you can go logging. You can click on space data, apply, okay. And you can do the harmonic spectrum. Like go to discrete. Here I have used discrete method because I just want to go for higher sampling time. And at the time of hardware deployment, I recommend you to go for discrete mode only instead of continuous mode, because sometimes this 28069 and all, they don't accept continuous mode of simulations. This is as per my experience. It may be true or not, but I'm just sharing my experience. So you can go for this. Let us take again a 5 minutes time. Then we'll go for multi-level inverters. You can go for the single